Good afternoon.
Yeah, let's go to Patrick.
The exam will be on Thursday, March 28th on Science Center Hall, room 247. Thank you. So we will start at 2:10.
Science
Center Hall.
Yes.
Yes.
Oh, thank you.
We'll start at 2:10.
Yeah.
Up to 3:30. All right. Any question before we start? Okay. Today we are gonna talk about columns, a new mechanical component, and how can we design columns. First, let's the mechanical typically it's a line and then the object subjected to compressive load. So if we have a line, typically line and cylinder subject, which is object which is subjected to compressive loading, we say it's a column. So if I have something like this, which is under tensile force, it's not a column, but if you have the same thing, but this time it's under compressive loading, we have column here. So the compressive loading is the key points on the definition of the column. So if we have this component, this mechanical component, which is under axial loading, if I ask you find the stress at the critical section would be any section in this component. So sigma would be force divided by the area. And if it's made of a material with the yield strength of Sy, we can say failure occurs when sigma equals to Sy. When the stress that you applied, it equals to the yield strength of that material. So, and when it happens, we can say failure due to yielding happens. Now, if I change this to the column by changing the tensile force to the to compressive load, I can say that sigma would be equals P over A, just compressive, and you can compare this with yield strength again and check if the failure occurs. But for columns, there is another mode for failure. So for the component which is under tensile force, the only failure mode is due to the yielding. But just imagine if you have a component like this, when you increase the load from 0, you increase the load. If this column is long enough, before you reach to sigma equals to sy, before you reach to this one, you might see some buckling, that we call buckling, happens in the column. So this is another mode of failure that we might see on the mechanical component, which is under compressive load, which we call column. So this is the buckling. So for columns, we might have two modes of failure. Failure due to yielding, or failure due to buckling. Again, when you increase the load from the zero by increasing gradually this force, at one point you may reach to a force that bending the column is gonna the column becomes unstable, and the bending moment develops rapidly. So we call it buckling, and then we have a failure on the mechanical component. So we would like to find this amount of the force in which the column is going to start buckling. So we call it P critical. How much would be the P critical for buckling? If I ask you how much would be the force for yielding, you can say force divided by the area, set it equal to Sy. The P critical for yielding is going to be Sy times cross section. In this chapter, this section, we are going to find the P critical there are 4 categories of the columns. Long columns, if they are long enough, with the load applied at the center of column, something like this. When the load is applied at the center of the column, it's a first category, or intermediate length column with the central loading. If we have shorter column but still load applied at the midpoint of the column, and the column with eccentric loading, if the force is applied offset, somewhere different than center of the column. We cover these two, we don't cover the last two categories. So we cover long term and intermediate length column with central loading. So for the columns, we might have 4 different end conditions. The end condition of the column can be in 4 different types. 1, pin. If you make pin at both ends, this figure is showing that end condition when we have 1 pin at one end and another pin at the other. So second condition would be 1 end fixed, another end is fixed. As you see, there is no slope here, there is no slope at the end of the column. So we have fixed, pin. 1 end fixed, 1 end is free, just something like this. You apply the force, or 1 end is fixed, the other one is pinned. So there is a slope at the end, but it has been fixed at the end of the beam. So we have 4 different conditions, and as you see, the length of the columns for all 4 cases are the same, but you will see that the critical load is going to be different for these 4 conditions. So the critical load depends on the end condition. We would like to find the P critical for the column. Suppose you increase the load and buckling just started. So the force, this is the critical force which made a buckling happens on the column, and we would like to find this. So if I cut it at, if this axis is X, this axis is Y, I just change X and Y to this direction and X to the other direction, because I would like to represent deflection by the variable of Y. So if this is the deflection of the beam due to the axial load, if I cut it at this cross section, like here, I have a force of P applied here. Since I have one force here, I should apply another force in the opposite direction on the other end. And this distance is Y. This deflection is Y. Force times distance is making moment in this direction. So I should apply moment in the opposite direction to avoid the rotation. So M would be P times Y. So this force is gonna develop one force here, internal force, and one bending moment at the section that I cut. If this is X, this is Y, positive Z is gonna be this. X, Z, and Y. Positive Z is gonna be this. So this moment is gonna be about negative of Z direction, is making my thumb is gonna be in the negative direction. So if I want to make a positive, if I want to consider the sign, it's going to be M equals to negative P times Y, because this moment is negative. What was the relation between the moment and deflection? M over EI was second derivative of Y with respect to X. We did it before the break. The second derivative of deflection is going to be M over EI. I'm just using this equation. And M would be EI, second derivative of Y with respect to X. Just plug in negative PY equals to EI, second derivative of Y with respect to X. What is the I? I is second moment of area. E is the modulus of elasticity. And what else? P is the force, Y is the deflection. Y prime is first derivative, y second is going to be second derivative. So if I replace here, I will get ei y second plus py equals to 0. It's a second order differential equation, homogeneous, because the right hand side is 0. We can solve for y. What would be the y as a function of x? What would be the deflection over the beam, over the column, sorry. The response for this is going to be C1 sine of s square root of p over ei x plus C2 cosine of s square root of p over ei x. It just, for the second order differential equation, the response is going to look like this. You have taken DFQ, so I mean, I don't go to the math, it's not difficult, but you can get the response of this differential equation look like this. C1 and C2 will be constant. They depend on the initial condition. Initial condition. At x equals to 0, which is this point, the y is 0. We don't have any deflection. So just plugging x equals to 0. Y at 0 would be C1 sine of 0 plus C2 cosine of 0. Sine of 0 is 0, so the term is going to be 0. Cosine of 0 is 1, so this is going to be C2. And this should be equals to 0, so C2 is going to have the value of 0. I rewrite this again, y of x, C1, C2 is 0, I only have these terms. Now, the second initial condition, at end of the beam, at x equals to L, if this is end of column, sorry, at the end of column, if it's the ending point of the column, the deflection, I can see the deflection is going to be 0. So one more time, apply the initial condition, sine of square root of p over ei times L equals to 0. C1 times sine of this should be equals to 0. C1 cannot be 0 because if C1 is 0, then the deflection function is going to be 0, which is not true because we have some deflection. So I should set sine of this equals to 0. So how it's possible if this equals to pi, if s square root of p over ei equals to pi. If this inside the parentheses equals to pi, sine of pi equals to 0, then I will get 0. So if this is equals to pi, if I square this, I will get p over ei equals to pi square. Then p critical is gonna is L square. I forgot this L. Square root of p over ei times L equals to pi. If I square both sides, I will get p over ei, L square equals to pi square. So pi square ei over L square. I will find the p critical as a function of pi, which is a constant, modular elasticity of the material, second momentum area for the column, whatever is the cross section, and the length of the column. And this is the force that I was looking for buckling. I squared EI over LS squared. Any question on this? Yes.
We're going to have to derive that equation for y for ourselves.
On the exam, you mean, or?
Just in general.
No, I just wanted to. I could just write this one, but you could ask me how did I get this physical force. So I wanted to show you the process how we get this equation. So yeah.
Is this applicable to both of the first two instances of columns? So long column with central loading and intermediate column with central loading?
Yes.
Okay.
You will see this equation is valid, but I'm gonna develop this for intermediate column. It's gonna be different.
Okay, so this
Because-
is just for long columns
yeah.
with central loading.
Theoretically, it should be valid for any kind of the column, but the test and experiments show that we have some failures on the short, on the intermediate column, so we need to use another equation for P critical for that kind of column.
Thank you.
Yep. And this is valid for pin. When I applied the initial condition, I said for the pin, at this point, we don't have any deflection. At the end of the pin, we don't have any deflection. So if I have one end fixed, one end free, what would be the boundary condition for this column? We need two because we have two coefficients. So think about two boundary conditions if I change this column to the fixed free.
Oh, that's true.
X equals 0, y equals 0. X equals L. So yeah, with that x y. So you can say this as L. I don't know what you use for That's it. No.
Any volunteer?
X for first initial condition, x equals 0, y equals 0.
Second,
The second, x equals L over 2 and y equals 0.
at the middle, you mean?
Yeah.
I mean, when you apply, when you have something like this, and you apply the compressive load, is gonna, if it's large enough, it's gonna make something like this. So the only point which cannot have any deflection would be x equals to 0. So you will see, although it's going to be small, but you are going to have some deflection over the column. So we cannot say at the middle or any other point that we have no deflection.
At x equals L, y prime equals 0.
At x equals 0, y prime is 0. I would like to say that. Here, when I have pin, if I ask you what would be the slope of the beam, you can say y prime is going to be a slope here. But for a fixed and at this point we don't have any slope at the starting point because it cannot have, it has been fixed. It cannot rotate about that point. So the slope is going to be 0. I mean, y prime is dy over dx. So if you, instead of these two initial conditions, if you apply these two, the critical force that you will get would be, P critical would be 1 over 4 pi square EI over L square. Fixed, free, pin. So it's quarter less than pin. So if I want to have a general function for P critical, I add 1c as a coefficient, and for different type of this columns, I will find that c. For pin, c is going to be equals to 1. For fixed free is going to be 0.25. For fixed, post and fixed is going to be 4. It's 4 times greater than pin. And for 1 and fixed, 1 and pin, it's going to be 2. So comparing these three coefficients, it's 4 coefficient, it's obvious that the fixed free is going to be the first column that you will see buckling after that because it's going to have the lowest coefficients. So as you see, the critical force depends on the end condition. So see. So the general function is going to be c pi square EI divided by L square. These values that we calculate are theoretical things. 1, 4, 25, 0.25, and 2. But there are some recommended value and conservative value for these 4 different types of the columns. For the fixed free and pin, they are not going to change. 0.25, 1 and 1 is going to be the same. But for the fixed and fixed pin, we got 4 and 2, but we are going to use 1 and 1 if you want to be conservative, but recommended value is 1.2 instead of using 2 and 4 for both. So these are just some applied value that you can use on your design. If you want to be more conservative, and or if you want to apply the recommended value.
Is rounded like
Pin, yes. Rounded, I mean, we have, yeah, these two. All right. So we call this formula as an Euler formula. So let me P critical equals to pi square EI over L square. Let me use the C. Yeah, yes, if we use the C as well. Euler formula for buckling. So I'm gonna keep this, get rid of so if we have circular cross section for a column, and I ask you what would be the I would be pi d power 4 divided by 64. I x equals to I y. For circular cross section, the second moment of area with respect to x and y are equals to each other, and it's gonna be pi times d power 4 divided by 64. I can write I equals to cross section area and k as a radius of gyration. Just represent I by this equation, a times k squared. For circular cross section, I is pi d power 4 divided by 64 equals to area. Area for cross section is pi d power 4 divided by pi d squared divided by 4 times k squared. So I can cancel out pi. These two. 16. So k squared is gonna be d squared divided by 16, or k squared is gonna be d over 4 for circle. For different cross section, you will find this radius of gyration. So what I'm gonna do, I'm gonna replace this I by a times k squared. Do some math. P critical would be c pi squared E a times k squared divided by L squared. I divide both sides by a, so P critical divided by a, load per unit of area. The unit is gonna look like, it's going to be same as the stress. Force divided by the area. Because it's not a stress, but they are going to have the same unit. Load per unit of area equals to c pi squared E k squared divided by L squared. I divided both sides by a. And then I'll bring this k squared at the bottom, so I'm going to get c pi squared E L over k square. We call this Euler buckling criteria. I didn't add anything to this, I just did some math, and instead of having P critical, I have force per unit of area, and right hand side, instead of having L and A, I'm going to have L and K. And L over K is defined as a slenderness ratio of column. Each column has its own length, each column has its own radius of gyration. So each column has its demonstration. So this P critical, as I said, is the force which places the column in a unstable condition. The buckling is gonna stop. So this is the definition of the P critical as we drive. Any questions so far before we do a class activity? Let's do some class activity. For rectangular cross section, you are gonna have different I for X and Y. It's different than circle. So find the radius of gyration about Y-axis and about X-axis. So IXX is different than IYY. So first find these two, then apply this and find KX and KY. Number 37.
It's me. Want a prize?
What do you think about KX?
Square root of h over 12b.
This?
Yeah.
Alright, thanks. IXX, I with respect to X, is BH cubic divided by 12. set it equals to A times KX squared. A is B times H, KX squared. I can cancel out these to B, and 1 of the H, I will get H squared divided by 12 equals to KX squared. So KX would be S square root of H squared divided by 12, or H over S square root of 12. So we don't have this. And KYY, IYY is going to be H B power 3 divided by 12. Instead of BH power 3, I will get H times B power 3 divided by 12. I will get B over a square root of 12.
So is that just the maximum amount in any direction that the column can buckle in? So like we've got in the pin one, we have it coming all the way around.
Yeah.
So like the radius of gyration of it, like how much outside of the neutral location it is, or like what does that represent?
Radius of gyration. A radius of gyration, I just use this to change the Euler buckling criteria from this form to this form. Then I define this as a slenderness ratio to compare different columns based on this criteria, L over K. So
So it's more of a tool and less of an indicator of what's actually happening in the specific column.
yes.
Okay.
Yep. And but you mentioned something that I was going to ask on the second class activity. Here, if you compare IX and IY, compare IX and IY, which one is greater than the other one? X is greater than IYY because B is less than H, so H power 3 is going to be greater than B power 3. So if you plug in here,
It's like maxed out.
P critical equals to C pi square E IX X divided by L square, and we find another P critical by plugging IY. So since IXX is greater than IYY, P critical for X is greater than P critical for Y. So it means when you increase the load, if this is a cross section, when you increase the load from 0, first you will reach to this one. So it means the buckling is gonna first occur about y-axis. So instead of x-axis, just think about rotating the column in two different directions. So it can rotate in this direction, or it can rotate in this direction, which is difficult to do that. So if you apply the force, the first thing which happens is going to be about y-axis because of this. And For this cross section, you are gonna see the buckling first about y-axis or rotating about y-axis. In this class activity, I was asking you if the length of column is 1 meter, what would be the critical unit load P critical over A, which makes failure in column with rectangular cross section. So P critical A with respect to x-axis is gonna be this C pi square E divided by L over Kx. P critical over A Y is C pi square E over L is 1, C pi square E divided by 1 over Kx square C pi square E 1 over K Y square. So Ky and Kx coming up, so P critical over Ax C pi square E Kx square. If you compare these two, C pi square and E are the same, the only difference would be Kx and Ky. Kx and Ky, right here. Ky is smaller than Kx, so this one is less than this one. So by increasing the P, the first buckling which happens is going to be about y-axis. So in any cross section, since we have two axes, we might have two different buckling. For circular cross section, since we have symmetry, we only have one buckling. But in the different cross section, we might have different buckling, and we should make sure that which one is gonna happen first. Now, what I'm gonna do, I'm gonna introduce this figure. This figure has y-axis equals to P critical over A, which is this, and x-axis is L over K. So L over K is x. So you will get something like this. And L over K is the slenderness ratio. And P critical over A is the unit load. We will discuss about this graph on Wednesday.